Module 9, categorical data. And up to this point, the kind of data, for the most part, that we have dealt with has been quantitative and usually continuous, and looking at the mean of those underlying populations and the standard deviation was made a lot of sense. But sometimes we have data where the variable of interest is not quantitative but qualitative, or sometimes called categorical. Let me give you an example. So to motivate some things, here is an example that we're going to work in a little bit on the second page. The drug Ziac is used to treat hypertension, and in a clinical test, 7 of 221 Ziac users experienced dizziness. And eventually we want to compute a confidence interval on a percentage, but there's numbers in there, obviously 7 out of 221, but the variable that's observed on every person in the sample is whether or not they experience dizziness. Okay, and so that's not quantitative. That's a qualitative variable. It's a yes or no response, and we think of this as qualitative or categorical data, or it yields categorical data, and we have certain techniques to analyze this kind of data. Okay, so intro paragraph here kind of spoke to that. Data obtained from these kinds or these types of variables are called categorical or count data. And if you think back with me on a previous module that dealt with data description, when we had this kind of data, we did look at data description there. You might describe the frequency of this kind of data with a pie chart, bar chart, this sort of thing. Okay. All right, so let's start here in the one sample case, one sample inference, and I want you to recall from a binomial experiment way back when we designated, so a binomial experiment had Bernoulli trials. Okay, remember Bernoulli trial, there's one of two outcomes there, a success or a failure. We designated pi, or here we designate pi as the probability of success and 1 minus pi as the probability of failure. And then this was the formula that gave us the probability of seeing little y successes out of a sample of size n. Okay, and so what we're doing here in this module is not using this formula to compute probabilities. Rather, what we want to do here is perform inference on this probability of success. Sometimes it's called the proportion of success or the percentage of success. But I want to tie back to what we've done before to what we're doing now. Okay, so thinking about the population proportion, pi is the proportion of percentage of the entire population. Just to be clear, it's the percentage of the entire population that is classified as a success. And so if you want to think back to our example here, it would be all people that use the Ziac drug. That would be the population, and the proportion of those that experience dizziness as a result of the drug, that would be our underlying population proportion. Okay, that's unknown because all we see from the data is the 221. That's our sample there. We don't see everybody that will use Ziac. But that's the proportion we want to say something about, or the percentage we want to say something about. And it's a parameter, it's unknown. Okay, so we estimate that with a sample proportion, pi hat, and it's the proportion or percentage of a sample that's taken from the population that's classified as a success. And the way we compute this pi hat is we take y over n, and y is the number of successes. Okay, pretty straightforward idea. So this is a point estimate for pi, and we have seen and we've talked at length about how point estimates are too rigid. They don't reflect sampling variability, and we need a more sure technique to do inference on an unknown population parameter. So we're going to look at an interval estimate of pi, a confidence interval here. In order to build that, I want to say a few things about the distribution of y. Now, y really is binomial, but it turns out that it can be approximated with a normal distribution when n times pi is bigger than 5 and n times 1 minus pi is bigger than or equal to 5. That's a rule of thumb that allows us to approximate the binomial distribution with the normal distribution. Okay, there's other rules of thumb out there. For us, we're gonna go with this. With that in mind, we can take y over n, which is pi hat, and approximate it by the normal distribution as well, and its associated mean and standard deviation are given in these two formulas here. So here, if you see, this is the mean of pi hat. It's saying the mean of pi hat is pi. That is, the average sample proportion is the population proportion. Okay, and the standard deviation of the sample proportion is given by this expression, the square root of pi times 1 minus pi over n. All right, so both these, this idea basically allows us to think about, again, this is the sampling distribution of pi hat in this case. So pi hat is approximately normal with this mean pi and this square root term as our standard deviation. Okay, so a confidence interval for pi can be obtained with this formula here. And where does this formula come from? Just to give you some insight, I'm taking pi hat, and if I subtract off its mean and divide by its standard deviation, then this thing is approximately standard normal for large N. Okay, and this is actually a central limit theorem result. When you think about what pi hat is, it is acting like a sample mean, because it's adding a bunch of zeros and ones, dividing by n, and so that looks like a sample mean. So the CLT kicks in. This statistic is the basis for a confidence interval estimate. All right, just like when we were doing inference on a population mean, this statistic was the basis for that inference. Okay, so let's see here. Let's look at this formula briefly. Notice here it's a point estimate plus or minus a z percentile times the estimated standard error or estimated standard deviation of pi hat. And so we're going to use that formula here. That's called the confidence interval for pi. Now it turns out that this interval can have what we say poor coverage properties when n is not that large. What we mean by that is that you may have a specified confidence level, and that informs what our alpha would be, but the actual confidence level is much lower. So for example, simulation studies show, and you can read about this in your textbook or elsewhere, that say if we're doing a 95% confidence interval, then our z sub alpha over 2 is 1.96, and we plug that in there. But if n is small, that the proportion of times this interval actually captures the underlying unknown or underlying proportion in simulation studies can be quite lower than 95%, even as low as in the 60s and so forth. And so that can be a problem, and one way to remedy that is another confidence interval formula, and that's what we have here. This is called the adjusted confidence interval. Sometimes it's called the Wald-Agresti cool interval, the WAC. But basically what this interval does, you can see the structure is pretty much the same, but what we do here is we first, instead of having pi hat, we have pi, that's pi tilde, and pi tilde is the number of successes plus 2 over n plus 4. And so thinking of how does that compare to the regular sample proportion, what we've done basically is we have added 2 successes and 2 failures. Okay, so same structure, added 2 successes, 2 failures. This is the resulting interval here for the population proportion pi, and I give you a reference on that particular interval. Okay, so with that in mind, let's tackle this example here. Again, what we are interested in, the parameter of interest here, is not a mean, not a standard deviation, but an individual proportion or individual percentage. So I'm going to write it this way. Pi is the proportion. By the way, you may have been thinking he's saying pi. Isn't that 3.14 with a few more numbers after it? So when I say pi here, I'm not referring to the irrational number that you've seen in geometry. But pi is the proportion of all ZIAC users who experience dizziness. Okay, and we want to say something about that proportion. You could imagine if you were the FDA, if you worked for the FDA, or if you worked for this company that made this drug, you would want to say something about this underlying proportion, as it is references a side effect of this drug. Okay, so we're going to use here, I'm going to use the adjusted interval. So I'm going to have here pi tilde plus or minus z sub alpha over 2 times the square root of pi tilde times 1 minus pi tilde over n plus 4. What I'm going to need first is this pi tilde quantity. And so if you look at the formula for it, it's y plus 2 over n plus 4. Here y is 7 and n is 221. Okay, so if you do the arithmetic there, you should get 0.04. Okay, rounding to the it's actually not rounded, but it's exact there at 0.04. So that's my pi tilde. In a sense, that's another estimator for pi, and I'm going to use that here in this formula. And so I've got 0.04 plus or minus the z value. So I'll let you look this up in the in your normal distribution table, but if you look up z sub 0.01 divided by 2, again we have a 99% confidence level. Z sub alpha over 2, or ultimately z sub 0.005, if you look that up, that's 2.575. Okay, so what I have here is 2.575, then times the square root of 0.04 times 1 minus 0.04, all over 221 plus 4. Okay, so simplifying here, I've got 0.04 plus or minus. That entire term that I've got circled there turns out to be 0.0336. And this term here is called the margin of error. We've referenced it before. But this particular interval in this inference procedure does have a margin of error. And the lower bound and upper bound are 0.00643, 0.0736. Okay, so that's our confidence interval on pi. So the way we would interpret this you could write it out. We are 99% confident that between, this would be between, what's that percent? 0.643% and 7.36% of all users of Zyac experience dizziness. Okay, so that's our interpretation of the confidence interval. So those are plausible values for pi. Anything outside that range we would see as not reasonable. Now that's not to say it couldn't happen, but it's just we're 99% confident that it's between these two numbers. All right, so highly confident there. A little bit more about this margin of error. It's defined as, again, that the stuff you add and subtract to your point estimate, which makes it the half length of the interval. So if we take this margin of error, and if we wanted to know the required sample size to have a particular margin of error for a particular confidence level, given a certain value of p hat, we would just solve for n. Okay, so just using some algebra, I'm not going to go through it, but you could solve for n, and this is the expression that you would get there. Okay, so and we would do that if we wanted to know a sample size required for a particular confidence interval with a specified margin of error. And so this is this sample size determination idea. Now the problem with this is that now here I have pi hat. Let me remove that. Well, I shouldn't. I mean, that's the margin of error, and here in the formula I have just pi. Now you could, if you wanted to write here pi hat, you could, but either way, the problem is before a sample is taken, you definitely don't know pi, and you're not going to know pi hat. All right, sample's not been taken. So what do we do with this? What do we plug in here to get a sample size that will give us a sufficient margin of error? You can substitute an educated guess, or you can use the value 1/2. Now 1/2, this is kind of neat within this particular situation. 1/2 actually maximizes this part of the formula, pi times 1 minus pi, and it gives it gives a conservative answer to the required sample size. So conservative in the sense that, maybe we want an interval of a width, of 0.05, and if we plug in 1/2 for pi there, we may actually get intervals of widths that are smaller than 0.05, but it will be no greater than 0.05. All right, so that's what I mean by conservative. Okay, so we can do interval estimation of a population proportion. We can also do hypothesis testing of a population proportion, and on this page I developed some of that idea. Here, notation is the same, except I've got this value pi naught. That's the null hypothesized value for the population proportion. Okay, and the assumptions here are that I have a simple random sample, really I should say, of binomial data. Okay, that's the kind of data we need. We need a binomial count from a simple random sample, and that would be that's when we could use this particular method. Okay, as well as the previous confidence interval. Now, we also need a quote-unquote large N, and that is governed by, again, this rule of thumb that we saw earlier. So with those in mind, we can perform three kinds of hypotheses: left-tailed, right-tailed, and a two-tailed test. So again, left-tailed test, pi is less than pi naught. Right-tailed test, pi is greater than pi naught. Two-tailed test, pi is not equal to pi naught. Here's our test statistic. What we do is basically we take this quantity that we had earlier, and remember that's sometimes called a pivot quantity. We take that and we substitute in the value of pi under the null hypothesis. And so that's what's done here. We put pi naught there, pi naught, and pi naught. We compute that. That follows an approximate standard normal distribution for large values of n. That is, when I say large values, again, I mean this. And so this is a technique to compute a test statistic, ultimately to run a hypothesis test on a population proportion. Now, my preference, and really my preference in most statistical methods, is to use a confidence interval instead of a hypothesis test. So you can actually use this confidence interval up here, and we've kind of spoken to this idea, this confidence interval formula here, to run a hypothesis test. That's my preference, but there's a place for using just the regular test statistic as well.